Today we are going to have a short discussion about mathematical induction. First of all, let's get to know about the definition of it. Mathematical induction is a powerful mathematical technique that is used to prove a statement or formula or theorem is true for natural numbers. Next, let's get to know the step that is involved in mathematical induction. First of all, we have base step. In the base step, we have to prove that the statement is true for n equal to 1. The second step, which is inductive step, we need to assume that the statement is true for any value of n equal to k. Then we prove about the hypothesis is true for k plus 1. And last one, conclusion. This is necessarily after you prove the first two steps are true. So in the conclusion, we satisfy the assumption that the inductive hypothesis is true. Now let's get to know climbing infinite ladder. There's a thing called ladder here that we can imagine. When we can reach the first step, or we can reach the first rung by stepping our first step, then we can also reach the next rung as well. So suppose we have an infinite ladder, we can reach the first rung of the ladder. If we can reach the particular rung of the ladder, then we can reach the next rung as well. If we repeat the process from 1 to step 2 to step 3 to step 4, and then we can also reach k step. Now let's move on to the next principle of mathematical induction. The induction principle is the domino effect in mathematics. The domino effect is the chain reaction consisting of a row of falling dominoes. So as you can see in this GIF, the dominoes fall from the first one, and then it will also fall the one that stands next to it until the last one, or the indefinite number that we don't see there. The domino here are the case of proof. When a domino has fallen, it means a base case has been proven. So as you can see from this GIF, when this one fell, the other that stands next to it also fell from one to another. When all domino is fallen, then the proof is complete. In mathematics, we can also consider indefinitely many dominoes. Now consider an infinite sequence of dominoes labeled 1, 2, 3 until the indefinite number which each domino is standing. Let Pn be the proposition that nth domino is knocked over. We know that the first domino is knocked over, then we can write P1 is true. We also know that whenever the k domino is knocked over, it knocks over the k plus 1 domino as well. Then we can write pk is true, then pk plus 1 is true for all positive integers k. Hence, all dominoes are knocked over. Pn is true for all positive integers n. Why is that? Because as we can get the proof from here, we have our base step proof, and we can assume from this case, and then we can then reach to our conclusion. Now let's move through the example. In order to get to know more about the induction, we should be able to visualize something. Our first example, we need to show that 3 to the power of n minus 1 is a multiple of 2. So as you know, the base step, we have to show that it is true for n equal to 1. If we substitute the number in, we'll get 3 to the power of 1 minus 1, which equals to 3 minus 1, and the result is 2, which is, of course, it's the multiple of 2. Now, for our next step, what is it? Well, it's the inductive step. So for the inductive step, we assume that the proposition is true for n equal to k, which then we will get 3 to the power of k minus 1 is the multiple of 2. As you can see here, this is the original proposition, and in case for n equal to k, we substitute n by k and we'll get this. Now, we need to prove that 3 to the power of k plus 1 minus 1 is also multiple of 2. It can also be written in this way, and you can also further write it in another form in order to get what we want. So as you can see, 3 to the power of k plus 1 minus 1 can be written as 3 multiplied by 3 to the power of k minus 1, which can then be further written to 2 to the power 2 multiplied by 3 to the power k plus 3 to the power k minus 1. So when you reach here, can you visualize something, or can you imagine of anything else? So I can tell you the clue here. We have 2 as the front number and multiply, which can also mean that it is the multiple of 2. And this one here, do you see something noticeable? Okay, so this one and this one are the same, which means that it can refer to this case. So this one is like explicitly we can see that it's the multiple of 2. And for this one, it is the case of our assumption which n equal to k. Yes, and then we can reach our conclusion that 3 to the power k plus 1 minus 1 is the multiple of 2, and the proposition that they propose is true. Now let's move on to the next example. Our second example proves that 1 cubed plus 2 cubed plus 3 cubed plus blah 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 until n cubed equal to 1 over 4 n squared multiplied by n plus 1 squared. Do not forget it, our first step, we need to show that it is true for n equal to 1. So when we substitute the number in, we can know that 2 squared is 4, multiplied by 1 is still 4. When it's divided by 4, we'll get 1, and this one is also 1. So these two are equal, and our case is true. For our next step, which is inductive step, we assume that it is true for n equal to k. Now, we will get this. From our assumption, we can replace k into this, and we assume that this is true. Now, after assume it is true, we have to prove that it is also true for k plus 1. For the case of k plus 1, it can be written as this. And from our assumption, we know that 1 cubed plus 2 cubed plus 3 cubed blah 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 until k cubed equal to this number, which we'll get it from here. And then what are we going to do next? Can you think of the next, the next process? Okay, so we have this one here, and we have this one here, which is kinda maybe give you idea what to do next. Okay, so what we see are this, the things inside this are exactly the same as this. So we are going to do a replacement from this that we are going to replace into this. And what we are getting is this, because we are replacing 1 over 4 k squared multiply k plus 1 squared into this one, and we'll get this. This one is still the same, and this one are still the same as well. So after we get this, we don't want to keep the division, and we want to multiply it in order to get this, and because it is easy to calculate more than the division. After that, we can factor this because we see that k plus 1 square can be factored from this as well, and this one, after we factor, we remove it, and then we get this result. After we get the result, we are going to multiply this, and these are what we get. And from what you can see, the result is k squared plus 4k plus 4, and this one is also give us same result, which means that is true. So in this case, we can reach our conclusion that the statement above are true. Is true. Now let's move on to strong induction. So what is strong induction? Strong induction is sometimes referred to as second principle of mathematical induction or complete induction. To prove Pn is true for all positive integers n, where Pn is a propositional function, we are going to do the similar step as the normal induction. For the basis step, we verify the proposition P1 is true. And next one, which is the inductive step, we show the conditional statement P1 and P2 and blah 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 until Pk is true, then we'll get Pk plus 1 hold for all integers k. Normally, when using the normal induction, we assume that Pk is true to prove Pk plus 1. However, in strong induction, we assume that all of P1, P2 until Pk are true in order to prove that Pk plus 1 is true. Now let's move to the example of strong induction. Prove that if n is an integer greater than 1, then n can be written as product of prime numbers. Let Pn be the proposition that says if n is an integer greater than 1, then n can be written as product of prime. For the base step, it is clearly stated here that n is an integer greater than 1, so we can start from 2. P2 is true because it's the prime number. It can multiply by 1 and it's only multiply itself. Like there's only itself that we can get this number. And our second step is the inductive step. So from our induction, that in the strong induction case that I told you earlier, we have to assume that all P1, P2 until Pk are true in order to prove Pk plus 1. That's why in this case, our range is from 2 smaller or equal to j and smaller or equal to k, because of that case that we talked about earlier. And we can consider two cases, but why two cases? Okay, so for the first case, we consider case plus 1 is already the prime number, which is already true. And the case number 2, k1 is a composite of prime number. Then k1 can be written as a multiply b, where a, b are in range from 2 to k. By the inductive hypothesis, a can be written as product of prime number p1, p2, blah blah blah, multiply pi, and b can be written as product of prime q1, q2 until qj. So all of these are prime number because it's clearly stated that it's the product of prime. So as we know that when it's the composite, it can be written as this, and then so k plus 1 can also be written as the product of prime from this two number combined as well, because from this is for a, this is for b, and when you are going to multiply these two, you'll get this. Then we can then reach our conclusion, which can be said that n can be written as product of prime if n is an integer greater than 1. So now I think it's your turn. and you may pause the video to do the exercise, which I'm going to show you like right after this. Okay, so we have 3 problem in total, which you can try by yourself in order to like get more familiar with the mathematical inductive. For the first problem, you need to show that 2 to the power of n plus 2 plus 3 to the power of 2n plus 1 is divisible by 7 for all positive integer n. The second problem goes by the statement, and also the third one as well. And I think the third one is a little bit more challenging, but you can try it out, because if you never try, you never know how challenging it is. You can screenshot or write down this problem on your paper and then just do it right away. Thank you for the attention so far. Thank you very much.